Imagine cruising calmly at 37,000 feet. Suddenly, without a single warning chime, the floor drops out from under you. In seconds, a modern commercial jet plunges nearly 1,000 feet. Passengers and unsecured objects are violently thrown to the ceiling, resulting in severe injuries and, tragically, a fatality. The drop itself is terrifying, but the screen sitting right in front of the pilots presents a deeper problem. This multi-million-dollar weather radar system showed absolutely nothing. The skies ahead appeared perfectly clear, right up to the exact moment of impact. They had flown straight into Clear Air Turbulence, or CAT. Conventional aviation radar is designed to bounce signals off moisture, specifically water droplets or ice inside clouds and rainstorms. Because CAT occurs in dry, cloudless air, there is nothing for the radar to detect. The turbulent air is completely invisible. This means our most advanced safety systems are unable to see one of the most violent forces in the sky. And it is a force that is happening more often. Commercial jets spend the majority of their flight time cruising between 30,000 and 40,000 feet, operating in the upper troposphere, where the air is thin and usually smooth. As greenhouse gas emissions trap more heat, the troposphere is warming up. This creates sharper, more extreme temperature differences between the equator and the poles. When these contrasting air masses meet, they create intense wind shear. Wind shear is a sudden shift in wind speed or direction over a very short distance, and it directly fuels the massive high-altitude air currents known as jet streams. Since satellites began tracking this in 1979, severe clear air turbulence over the North Atlantic has increased by 55%. Atmospheric researchers project that by the year 2050, the amount of severe turbulence on major flight routes could double. What used to be a rare atmospheric anomaly for flight crews is shifting into a persistent, everyday operational reality. To understand how this impacts an aircraft, we have to look at the exact moment a plane crosses into the boundary of a jet stream. Inside the jet stream, air can move at over 110 knots. When this high-speed tunnel of wind brushes against slower, static air, it acts like a fast-moving river dumping into a still pond. This boundary creates chaotic, invisible eddies that roll and tumble. When a plane hits this invisible wall of tumbling air, pilots have one immediate physical defense. They configure the aircraft to its specific turbulence penetration speed. By intentionally pulling back the throttle and reducing their airspeed, the crew minimizes the aerodynamic forces acting on the airframe. Flying too fast through these violent vertical updrafts and downdrafts would drastically increase the physical stress on the plane's wings and fuselage. Slowing down keeps the aircraft intact, but it is entirely reactive. To actually solve the problem, the aviation industry has to find a way to see the rough air before the plane flies into it. Aerodynamic mitigation prevents the plane from breaking apart, but reacting after the fact doesn't change the reality that the pilots are still flying blind. The first major step forward relies on data. The International Air Transport Association launched the Turbulence Aware program, a network where thousands of commercial aircraft automatically share real-time sensor data. As one plane experiences a jolt, its computers immediately upload the exact coordinates and severity to a crowdsourced, live map warning trailing aircraft of the invisible hazard ahead. But the ultimate goal is detecting turbulence in entirely empty airspace. To do that, the European Delicat project tested a hardware solution. They equipped a research plane with a high-power ultraviolet LiDAR system that fires a laser beam up to 15 kilometers straight ahead. LiDAR stands for Light Detection and Ranging, a remote sensing method that uses pulsed lasers to measure distances and properties of the atmosphere. Instead of looking for water droplets, this ultraviolet laser measures tiny fluctuations and the density of the air itself. When air parcels move rapidly in a turbulent zone, the laser detects these molecular shifts and bounces a scattered signal back. This dispersion graph from the Delicat flight tests shows the system's noise characteristics over time. By averaging the backscatter measurements over tens of seconds, the system's random noise steadily trends downward, isolating the sub-percent density fluctuations that indicate moderate turbulence. Combining a global network of shared fleet data with experimental laser optics, the aviation industry is finally building the eyes required to see the invisible. Before these lasers become standard equipment on commercial fleets, the vast amounts of sensor data collected today are being routed into massive computing centers. Airlines are taking millions of these real-time turbulence reports and feeding them into predictive artificial intelligence. This allows flight dispatchers to forecast high-risk zones and reroute flight paths hours before a plane even leaves the tarmac. And even with the rising frequency of rough air, modern aerospace engineering is incredibly resilient. Commercial aircraft are tested under physical stresses far beyond what they'll ever encounter in service, making an actual crash from clear air turbulence exceedingly rare. However, because these invisible pockets can still strike without a moment's notice, the ultimate defense for the person sitting in the cabin remains decidedly low-tech. An aircraft fuselage acts like a seesaw in the sky. If you are seated at the extreme ends, all the way in the front or the back, you will experience far more violent vertical movement than the passengers seated securely over the wings. This is why aviation safety investigators are absolute on their advice. Passengers need to keep their seatbelts fastened and pulled snug across their lap at all times, regardless of whether the overhead indicator sign is illuminated. As the warming planet shifts the physics of the upper atmosphere, the clearest horizons may hide the most violent air, requiring a constant, practical habit of safety from everyone on board.